I suppose if today is the 10th, Wednesday would be the 12th, 2020 is our in-class exam 1. And we will talk more about that at the end of lecture period today. You all have an assignment that's due before I walk out of this room, which is your 2 suggestions for testable problems. Today we're going to move on from our discussion of data classes in MATLAB to an introduction to another type of data class. When we spoke last time, we were talking about the, what were we talking about? What were we talking about last time? Yeah, 2's complement for signed integer representation. So far, all that we've done has focused on what type of integer, what type of number, sorry. I guess before I start this whole thing, let me ask the following. 1, is anybody on YouTube and can confirm that sound is working? Sound's working and it's not bad? Okay. And then the second thing that I would ask is, what questions, comments, or concerns do you have that you'd like to share right now? About just anything that we've done from lessons 1 through 4. All right, great. All right, so thus far, what have we studied? We've studied 8 data classes, which were what we call native numeric data classes in MATLAB. What were the 8 data classes that we studied? Yeah. All right. So we had what we called, let's see if I can get this thing. There it is. We had what we called unsigned data. What's the mathematical representation for unsigned? Oh yeah. So the idea would be that it is what type of data is encoded best with unsigned integers? Non-negative integers, right? And then we had this concept of uint 8. Next one was uint 16, uint 32, uint 64. What was the other? And in particular, all of this stuff we spoke about in which lesson? Yeah. So this was all in lesson 3. All right. What was the other type of data that we encoded? Yeah, take away the un. Okay, so we call this signed data. And right now our signed data, instead of being non-negative integers, we switch to the entire set of integers, yep. And we had 4 classes there, int 8, int 16, int 32, and int 64. All of that stuff we spoke about in lesson 4. You remember the whole concept here? Every single one of these data classes encoded signed integers in what representation? Yeah, we call that 2's complement. These things were just unsigned binary. Let's think about where we're going to go from this. And I suppose this is going to be page 1 of today's lesson. Here we've got page 2. It is still Monday, the 10th, 2020. I don't know, 10:10. So let's just go ahead and think about the mathematical representation of number systems. What were all the number systems that we had? The smallest number system that we studied formally was called the natural numbers, yeah. And then in this class we actually introduced the non-American or the French number system. And when I spoke about that, I had forgotten that at least one of you has a French parent. I know that now, right? And then we go up to the integers. What's next? Yep. Once we have rational, we also have real. Within, yep. Okay. Let's go ahead and think about this for a second. This thing right there, what's it called? In computer science lingo? Yeah, so that's called unsigned integers. This one's called signed integers. Could you guess what we're going to do next? Yeah, okay. Could you guess what fixed points are used to do? So let's just follow our nose here. We start lesson 3 with unsigned integers, and then we go lesson 4 to signed integers, and then yeah. This thing we're going to call fixed point and floating point representations. And we'll talk a lot more about that. This is going to be lessons 5, 6, and 7. And in fact, I would beg to make the point that this actually sets the foundation for all of numerical analysis, which is a fundamental pillar of scientific computation. Right? Okay. So, let's go ahead and think about fixed point representation. And to do this, so this is 2/10, 2020. Wow, that was 3-minute page. That's really fast. Okay. I think I'd like to start with an example. I didn't hear what you said, Taylor. Yeah, it's. Oh, yeah, right. Yeah, but not all people have taken my calculus classes, right? So let's go ahead and look at the following number. So let's look at 1101, and then maybe we'll do something like. You all like it when I do examples that are different than in the notes, right? Okay, so let's just toss a 0, 1, 0, 1. And let's think about that as a base 2 encoding. If that is a base 2 encoding, how many total digits do we have, binary digits? Yeah, so this is what we call an 8-bit representation. And then we can encode, if we'd like, the concept that each bit represents a position. And when we thought about, I don't know how you like to call nibbles. So this, we could call this one nibble. And we could also call this another nibble. And then if we were to impose meaning, how would I interpret this as an unsigned integer? Yeah, so what we would do is we say to ourselves, like, okay, let me go ahead and just add from 0 to 7 b sub I times 2 to the I, right? So let's go ahead and think about that for a minute. I don't know, do you want to do it from big endian or little endian? Do you want to read left to right or do you want to read right to left? Right to left? Okay, so how many ones do I need? 1 plus no 2's plus 1 4, 0 8's, 1 16, 32ths, 64ths, 128. Looks like those two together is 80, 208, 212, 213. Is that right? Okay, so now I'm going to do something that should make you yell at me, okay? What did I just do? What did I do? Say it again. Oh yeah, I did add an extra digit. But I want you to think about this. You're right. It's more precise. It has more detail. But the moment that I go from this representation to this representation, I break something. What did I break? This representation right here, especially using this map, what's the assumption? It's an unsigned integer. So actually, is there any ever use to doing a point something at the end of an unsigned integer? No, why? We'll never use it, right? But the moment that I drop that on, what does it then allow me to start doing? Transitioning from the possibility of only unsigned integers into the possibility of fractions, right? So this leaves the possibility of a fractional representation. And I guess Dorothy would say, we're not in Kansas anymore, right? Anymore. Hey, I like it. So what I want to do actually is take a look at the following number. I want to start understanding what does this look like and how do we represent. So let's talk about something called decimal fractions. And we're going to start with the easiest example that we could imagine, which is actually not so easy unless you've spent a few hundred hours thinking about it. Which in this case, all of you have spent a few hundred hours thinking about this stuff, which is really nice. Over the span of your lifetime, right? So let's talk about decimal representations of fractions. Okay, so let's let some number y be a rational number with y greater than or equal to 0. So what's my assumption here? The moment I put that representation on, what does it mean? non-negative. If I'm going to assume that we represent non-negative, could you guess what we call the type of representation? Unsigned. What does it mean to say that y is in Q? Yeah, so the numerator becomes a... Yep. And then one of my Math 105 students just on Thursday taught me this. One of them is the dividend and one of them is the divisor. Do you know which one's which? Yeah, you would think that mathematicians could freaking decide on what they're going to call stuff, right? So apparently the thing on top is dividend. Some people also call that a numerator. The thing on the bottom is called a divisor, also known as a nominator. This one I knew. Dequotient. That one's called dequotient. Thank you. Not funny, Anderson. With P and Q, in this case, must both be integers. And what do we immediately say about Q? Q for sure is non-zero. This representation we're going to call the fractional representation. Could you guess why we call that a fractional representation? Because it's written as a fraction. We could also write this as P divided by Q. I've never named this representation. Does somebody want to give this representation a name? Yeah, we could call that the, all right. Yeah, we could call it the quotient representation. Okay. Let's take a look at an example. So I think I'm going to do a new page here. So this is Monday, the so let's look at example 5.3, and Shayon has voted that he wants me to do an example that's different than the ones that I did in the notes, right? And since Shayon is my boss at this moment, I'm going to go ahead and look at 3, 1, 4, 1, 6 divided by 1, 2, 3, 4. We'll go ahead and call that y. What do we know about that y? What set does it come from? Yeah, and I really haven't figured out how to write unsigned rational numbers. In fact, yeah, you could, but then, like, does Q sub... I mean, you could do something like that, right? But I haven't spent more than an hour thinking about that exact notation, and so I don't want to do it off the cuff because notation matters, right? So for sure it is part of the rational numbers. So let me ask you this. How would you represent that number not in fractional notation, but instead in decimal notation? What is that number in decimal notation? 3.1416. Okay, now I would like you to infer generalized decimal representation of what this should be. Could you guess what we call the leading digit? What index might be used for the leading digit? How did we index numbers in unsigned and signed representation? The subscript on the index corresponded with what? Maybe we need to go back and think about this for a minute. So let's go back here. This is exactly why I started with this. 2, so let's think about it this way. How do I represent this in general decimal format? Why did I choose D2, D1, D0? Because each subscript corresponds to the corresponding power of 10. Did you get some good sleep last night? You look like you slept well. I mean, both emotionally look like and physically look like you slept well. So that's awesome. Okay, so what did we do here? What was the whole concept of each of these digits? The index on each digit corresponded with the power of 10 associated with that digit. So what would we call the leading digit here? D0. This thing we're going to call the radix point. So in the case of base 10, what type of point is this? Decimal point. In the case of base 2, we might call that a binary point. In the case of base 16, we might call that a hexadecimal point, or we could just call it a radix point and not get bogged down with details, right? Okay. What would the next digit be? D to the -1. And then D to the -2, and then D to the -3. And we should probably mark out what these are. D naught was 3. D -1 was 1. Oh, excuse me. What's the last one? D -2 was 4. D -3 was 1. D -4 was 6. Okay, let's go ahead and decipher what the hell I'm talking about. What am I talking about there? I'm running out of room. What does a professional do when they run out of room? No, that's a rookie. Okay, let's think about what this is. What is 3.1416? It's 3 plus 1 divided... Oh, yeah, I guess... No, you're way cooler than I am. I mean, but that's just true in general, right? You didn't even pause. You just said, yeah. God, that's hurtful. Now what? Okay, let's think about what that is. Could you write that in fractional form? So that would be, yeah, let's just start with 3 plus what? 1 divided by 10 plus, we'll get there. 4 divided by 100 plus 1 divided by 1,000 plus, okay, anybody see? Yeah, so I might call this 3 times 10 to the 0 plus 1 times 10 to the -1 plus 4 times 10 to the -2 plus 1 times 10 to the -3 plus 6 times 10 to the -4. But what's that? Well, let's go ahead and go back to our original notation. What was 3? And now you're going to see why I was so particular about teaching you something you thought you already knew, right? And we're just going to keep going deeper and deeper down this rabbit hole. And then because my pen is wide. Okay, well, what is that representation then? let's write it out in terms of our summation. What's the summation? Lower bound of the summation would be -4. Upper bound of the summation would be 0. Each individual element is d sub I times 10 to the I. Another way to write that is d naught radix point d -1, d -2, d -3, d -4. Okay. Anybody see something that is unique now to this number compared to all other numbers that we have spoken about? And maybe I'll help you define unique. Oh. I don't know, maybe these two. Claim. There is something fundamentally different about the things in green versus the things in orange. What's different? Okay, I want you to use the word fraction and integer. Shayan's got it because he said it. I mean, Shayan actually had a really deep thing. You said one of them was non-negative and one of them was... Yeah, so could you guess what we call the thing in front there? If I just truncated this thing and captured the thing up front, what would it then become? Integer. So we might call that first part what we call the integer part of our number. If the first one is called the integer part, someone please guess what I'm about to say. Okay. Yeah, we might call that a fractional part of the number. Okay. Do you want to do another example, or do you think you're ready to level up? You think you're ready to step it up? If I were you, I would choose another example, but I love the courage. Okay. All right, so let y be in Q. Okay. Could you guess how we write a general decimal representation of any fractional number? Let's not assume that the leading integer part has only one digit. What did we assume? What did we call the... so if we look back here, what did we call this? Integer part. Maybe we say to ourselves that it has I plus 1 digits, I for integer. So if the leading part, if the integer part has I plus 1 digits, what is the index on the most significant digit? Yeah. D sub I minus 1, all the way down to D1, D0. This whole thing, I don't think I have a green pen with me. That's really sad. Definitely don't have an orange pen. What do we call that thing? Yep. So this is what we're going to call an I plus 1 digit. What type of digit? Yeah, decimal digit, right? So we'll call that an I plus 1 digit decimal digit. It's a decimal digit because each of them is a decimal of the integer part of our number. Okay, so I represents integer. So let me ask you this. I shaved my beard this morning and cut my face in 50 different ways, so I really shouldn't be able to stroke my beard to think, right? Because I have no beard to stroke. Could you guess what we might call the last digit in the fractional part? The integer part we used I. D sub f. So what's the first digit? D sub negative 1. This is why I would have chosen to do another example. What's the last one? D sub negative f. We'll let orange be the integer part, and I guess I should like make it clear that this is what I'm talking about, right? Okay, and then we'll let green. Could you guess what we're going to call this one? Yep. Say it again. Yeah, that's crazy, right? So this is an F. I'm sorry, I didn't hear that. Does anybody see a natural question that arises? Let me ask a different question. Will this always be exact? I would not make that conjecture.
No, it would not.
What's the question? Okay, so yeah, you're not ready for the question yet, but you're ready for some observation. That's awesome. So the first observation that you made was what? Oh. Very interesting. Okay, so note. I guess we call that observation. I don't think I spelled that correctly. One divided by 3 causes problems. Why? One divided by 3 is equal to what in decimal? Zero point 3333333, which means if I choose any value of f that is an integer, what happens? That representation will necessarily be inaccurate. Does anybody see a theme in digital computation that arises at this exact moment in time? How much memory do I have on a standard computer? Another question, infinite or finite? Finite. How many bits would I need, forget bits, how many digits would I need to store this number exactly in this format? How many? An infinite number, and yet I have a finite computation machine, which means I have finite memory. What's the theme? Say it again. 1 plus 1 equals 3. The moment I choose to store this number in this format on a machine like the one sitting in front of me, what immediately happens? The number that I store will be inaccurate. In fact, it will be a approximation of that other number, right? So, could you give me some other examples of numbers that cannot be stored exactly? Could you give me a number that has, so in this case, this would be like d naught, d negative 1, d negative 2, and goes on forever. And in fact, I think in Math 1C, we've actually dealt with these numbers before. One of the reasons that we do sequences in series, right? Yes. So we talked about this thing as like a sub I times 10 to the negative I, right? And the claim was we needed an infinite expansion because the moment that we chopped off the expansion, it would no longer be accurate. So this is actually a calculus phenomenon, right? Okay. So could you give me a number with 3 decimal digits in the integer part whose fractional part requires an infinite number of digits and whose divisor is not 3? Okay, you're going to have to speak a little louder. So this is going to be called the Josh example. I mean, it doesn't have to be Josh, it's just... Yeah, for sure. 1/9 is a power of 3. That's not fair. Give me something. Give me something. Because that's it. 1/7. Thank you so much. I appreciate that. All right, so you're telling me... so let's let y be equal to, what was it? What was your integer part?
We can make it 777.
Okay, 791. Awesome. Plus 1/7. You sure 1/7? 3 7s. All right, that's kind of exotic. Okay, could somebody please tell me the fractional representation where you're not doing a mixed fraction? Because I think some of my students might say, well, Jeff, you could write this thing like this, right? But in a fractional representation, I want a pure numerator and a pure denominator. I don't know how to do that math.
5,540 over 7.
5,540 divided by 7. That looks kind of innocuous, right? I wouldn't run away from that on the street if I saw it. Okay, could someone give me the corresponding decimal representation of this sucker? Wait. It's 42857. Anybody guess what's going to happen next? Okay. And then we call this thing up here, what did we call that thing? Okay, so this whole thing right there is called the integer part. What did we call the thing in between? Yeah, I would specifically name it the radix point because it is a point, right? Europeans like the little comma, which I'm not against necessarily. This thing right here, what do we call it? Somebody see something very interesting about this fraction? Fractional part, I mean. You're going to have to speak a little louder.
Decimal fraction?
I was speaking about whoever spoke over here. No, you're all good. You do a really good job of not speaking very softly, which is awesome. I love it. Repeating. Okay. So we're going to do something right now which actually shows me what the general representation. So go ahead and give me the general representation of this thing using the D format rather than the numeric format. So what would the leading most significant bit be indexed by, and then go all the way down? Okay, D2, D1, D0, and then this goes on forever, right? Okay, so let's go ahead and look at this thing. Let's go ahead and look at the sum from I goes from 1 to, excuse me, this one's kind of interesting, isn't it? How would we write this? What is the upper bound for that sum? 2. What is the lower bound? Try that again.
Nice.
Yeah, I suppose we should.
Flip that around.
Well, MATLAB doesn't die. It's just that anytime we use MATLAB and we're not doing a symbolic manipulation, what we get is numerical nonsense. It's not exact mathematics, right? Yeah, and we'll talk. That's a major theme here. Okay, so here's a claim that I make. Any infinite repeating decimal representation encodes a y in Q. What did I just say? What was the thing, Kenny, that you noticed there? Okay. It repeats after a certain amount of digits. So in this case, we would see, we could actually chunk this thing, right? There's chunk 1. There's chunk 2. Could you guess what the next chunk looks like? Yeah, go ahead and just read out the next chunk for me. Yeah, 428571, 428571, 428571. Okay, so I just made a very interesting claim. Read this claim again for me. How many have heard this claim? That if you have a repeating decimal, you always know it's irrational. How many of you could prove that claim? We're about to do it. And you might ask, why do I care about this? And I'll show you in about 3 lessons, two lessons. It's not, many of my students think they know this. I did not know this. Up through my graduate years, I did not know this. Okay, so let me ask you this. Let's take an example here, and then we will. So let's take this number, and this one I'm actually going to do. I don't know. Yeah, let's do something that you've not seen before. Maybe we do 987.6.54321. And then I don't know, how many repeating digits do you want? 3, 4, or 5? You want 3 repeating digits? Have you ever seen that line above that says that means that we have an infinite number of 3, 2, 1s?
Yep.
Okay, so here's a claim. This number can be written as a rational. That's what this claim, this is a conjecture until we prove it. Okay, so what would you need to do to get this decimal point so that it is right there in between the 4 and the 3? So, yeah, by claim, y is in Q. In order to prove this, we, I guess, want to show that y can be written as P divided by Q with P and Q in Z. Okay, so what did you say? How do I get that decimal point in between the 4 and the 3?
Multiply by 10 to the power of difference in digits.
Okay, so 10 to the 2 times y would be 9, 8, 7, 6, 5, 4, point 3, 2, 1, 3, 2, 1, 3, 2, 1, off to infinity, right? How would I shift that point 1, 2, 3 to the right? What would I have to do to y to get that point right there in between the 1 and the 3 right there? Nicely done. So you told me that 10 to the power of 5 times y would be 9, 8. This is kind of a fun number, huh? Huh. Whoever wrote this number must have had some time for themselves. What do you notice about the second number minus the first number? So what do you notice about 10 to the 5 times y minus 10 to the 2 times y? What happens? What happens there? Use the word, the phrase fractional part. Say it again. Fractional part disappears, right? And what are you left with? 9, 7, 6, 5, 4, 3, 2, 1 minus 9, 8, 7, 6, 5, 4. What does that immediately mean about y? Can someone give me a value of that subtraction? I mean, hopefully you all have MATLAB up and running so you could just do this quickly, right? I'd like to know what, I mean, it doesn't really matter, to be honest with you. I guess I could rewrite it. All right, in the next line, I'd like somebody to be able to read what that value is out for me. I don't have my calculator. Okay. Am I doing too much? I think I'm doing too much for you. I think you need to suffer a little bit more. Just read the bit string.
9, 8, 6, 6, 6, 6, 6, 6, 6.
How many sixes? 6 sixes? All right, awesome. How about on the bottom? 10 to the 5th minus. Okay, and what would that number be? So now I've got 9, 8, 1, 2, 3, 4, 5, 6. And what do I have on the bottom? I think there should be 3.
There was an extra 7 at the end. So one.
Oh, this 6 sixes and 1 7.
Not rounding.
Awesome. What about on the bottom? My guess, without looking at it, is 3 9s and 2 zeros. Ten to the 5th minus 10 squared. I wish. I agree that if the thing was division, then indeed it would be 10 cubed. But subtraction is much more of a hairy beast, right? 10 squared. Yeah, 3 9s and 2 zeros, right? Beautiful. That's a beautiful mistake to make. Okay. So now, question. Did my claim come to fruition in this case? Is it true that y, in this case, with an infinite repeating decimal, is indeed a rational number? Okay. How many of you have finished 1C? How many of you have not yet finished 1C? So everybody in this room has finished 1C? I didn't see anybody raise their hand. I don't know if you want to see the geometric series conversion between these. How many of you would like to see that today? So a different algorithm to convert infinite repeating into...
Yeah, I've never done
Okay. All right, so this is one mechanism that will always work. And in fact, we're going to actually do a proof associated with this. And I promise you this is going somewhere quite deep. It's going somewhere in the 1990s. This is, in my opinion, all prerequisite to storing a single numeric variable. Okay, so let's take a look at this number again. What was the number? So this was proof 1. Let's look at proof 2. And proof 2 actually depends on Math 1C. It's almost like Math 1C is useful outside of the Math 1C classroom. So let's let y be equal to 9876.54321, 321, 321, infinite repeating. Okay. So now what I'd like you to do is tell me which of this number is non-repeating and which of them is repeating. So break it into, so 9876.54 plus what? 321, 0.321 plus dot dot dot. Okay. Okay. I was just checking to make sure you were awake. At least 2 of you are awake. And a few of you are skeptical, which makes me very happy. Okay, now what? 9876.54 plus 321 over 10 to the what? Plus 321 over...
5 plus 8. Or 5 plus 3.
yeah. Okay, what's next?
5 plus 3 plus 5 plus
10 to the 11 plus dot 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 dot. Okay, so this now is what? 9876.54 plus sum from... Yeah, my feeling would be 0 would be kind of nice, wouldn't it?
Yeah, because then we just math.
So now we've got what? 321 over
10 to the power of k plus
3k plus 5, right? And then maybe we need a review. We're going to call this geometric series. This is one of the reasons why I had my students memorize this, though many of them probably have forgotten. I'd like you to sum from k goes from 0 to n, r to the k. So just write out what that sum is, please. R to the 0 plus R to the 1 plus R2 plus all the way to r to the n. What's another way to write that? 1 plus r squared plus r cubed plus dot 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 plus r to the n. What would that immediately mean if I multiplied that entire thing by r? Okay, and then why don't I do 1 minus... Okay, so what's that now? So this is r times Sn. First power gets what? R to the 1. Second one now gets r squared. The n minus first term gets what? The nth term gets... Okay, what does that immediately mean if I take the original partial sum so
cancel out except for the first one.
yeah, let's go ahead and just look at term number. So we'll call that term number 1, term number 2, term number 3, term number n minus 1. We'll call that term number n, right? Okay, let's look at term number over here. Okay, this is term number 1, term number 2, term number n minus 1, term number n. What happens when I subtract? Away from blue, red.
What happens to your R0?
So R0 stays.
Everything else are
Terms 2 through n minus 1 telescope, right? So then I've got plus r to the 1 minus r to the 1. R squared minus r squared. And I just keep going. N minus 1 minus rn minus 1 until I get to the last term, which is what? Rn, is it positive or negative? Must be negative. What happens to all of these internal terms?
you have a red marker, you cross it out.
Each of those things goes to 0. Almost like a telescoping sum, except completely different, right? What is r to the 0? 1. This thing now is r n plus 1. How about on this side?
You gotta do some factoring by cancellation.
Okay, so what does that immediately say about Sn, which was supposed to be the sum from k goes from 0 to n of r to the k, which is 1 plus r plus dot 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 plus r to the n. What is that equal to? 1 minus r to the n plus 1 divided by 1 minus r.
Take a scalar at the beginning of the answer.
Yeah, I'm not tripping about that at the moment. So then what would that immediately say? We'll get back to our example in just a second. It's part of the reasons that why we're training you to take so many math classes. Well, it can matter. Just like, you know, my statement about math is it's like vegetables, right? You could design a life where you never eat a vegetable. True? You could design a life where you don't use math. It's not hard. It's actually harder to not eat vegetables than it is to not use math, right? But the analogy is, I find it to be the same. If you lived a life with no vegetables, what would you say about that life? That's the same feeling I have when I see how easy it is for society to help people design lives where they don't use math to do work, right? So here we go. What would you say now if I took how do you deal with a summation with a infinite number on top? Yeah, so you would say this is the limit as k goes, sorry, k is not a good one. What would you call instead of k? N, that was a,
Goes to infinity, k is 0 to n.
yeah, I think we call that improper, right? An improper summand. What was this thing again? If I have a limit, just look right here. What do we call that symbolically? Partial sum, right? That's what we call that in Math 1C. What did we know about S sub n? What was S sub n equal to? 1 minus r to the n plus 1 divided by 1 minus r. What would you say if the magnitude of r was less than 1? What do you know immediately the limit as n goes to infinity of r to the n plus 1 should be? Here's another way to ask this question. How would you like it if the people at your bank took the number, I don't know, 9 over 10 and multiplied that number by your bank account 1,000,000 times?
I would have a conversation with them.
Why? What's going to happen if I take a fraction and multiply that fraction by itself an infinite number of times?
Any fraction or a fraction?
A fraction that is between -1 and 1 and doesn't touch the endpoints. That thing goes to 0. So then what is this limit as long as I know that the ratio r is less than 1? What do I immediately know about this limit? One divided by 1 minus r. Okay? So let's go back here. Is this identical to that? What would I need to do to make this sum right there identical to that thing right there? Anybody see a really, really fast way to do it? What's one thing that I could bring out immediately? What else could I do? Yeah, I could bring out a 10 to the 5th. How about 3k? I need r to the k. What could I do there?
Product to the powers, and you can factor it out in the operator.
Okay, so we could call immediately r is 1 over 10 to the k. This thing is an a, right? So we could have done our entire derivation with a scalar in front. Oh, sorry, it's not 1 over 10 to the k. What is it? 1 over 10 to the third. Another way to say 1 over 10 to the third is 1 over 1,000. Okay, let's think about that for a moment. What do we know about the improper fraction when we have an infinity on top? What could we do with that? Turn it into a limit. The whole point here is in that limit. That I'm actually using a theorem from Math 1C right now that says if I have the if I have a scalar multiple times any convergence to series, I can bring the scalar outside or I can bring it inside. There's no cost to that, right? So this is now 1 over 10 to the third to the k, which is identically the thing that I was looking at, 976.54 plus 321 over 10 to the fifth. What is that limit? 1 over 1 minus 1 over 10 to the 3 by the geometric series. And we'll take a break at this point, and when we come back, we're going to finish up with a proof. That will be the end of today's work. Could someone get me a concrete formulation of this thing? So one thing that you could do immediately, so what is this? 321 over 10 to the fifth times, I suppose this is going to be 10 to the 3 minus 1, right? And on top it's going to be 10 to the 3. Is that right? Okay, so this would be 987654 over 10 squared plus 321 over 10 squared times 1 over, I think that's going to be 999, right? So this thing's going to be 987654 over 10 squared. And then this thing is going to be like 321 over 3 9s and 2 zeros. And then what would you do to add that together?
Please count the denominator.
Yep. So you'd multiply by 999, 999, and the claim is that this is now y. That is another way to get to the standpoint that anytime I have a repeating fraction, that repeating fraction for sure is a rational number. Okay. Let's end here for today. It's 11:12. What time are we going to be back? For session 1, I mean. 11:22. At 11:22, we're going to finish up our discussion of rationals. And then at some point soon, we'll get into fixed point representations. Pause. See you in about 10 minutes.